My name is Taka Shinagawa. I'm a field solution architect at the Google Cloud, specializing in Gen AI. Today, I'm excited to share a practical guide on performing remote LLM inference with Apache Beam using Gemini and Gemma on Vertex AI. So here's the agenda here's the agenda for the next 20 minutes. I will start with the motivation for remote inference. Then I walk you through the core technologies involved first, review 3 different implementation patterns for remote inference, introduce you to implementation with RunInference with new remote model handler subclasses, and finally wrap up with a summary. So bear with me before lunch. Why do we even need a remote inference with Beam? Let me just clarify the motivation here. So let me start with the limitation and challenges of running models locally within Beam workers. Running a model locally inside the Beam workers seems simple at first, but you quickly run into issues, starting with scalability and resource constraints. Today's models could be big, often exceeding a local worker memory. And hardware complexity is another reason. You might need expensive GPU on every single worker and the multi-GPU setup. This leads to cost inefficiency as you pay for the hardware even when it's idle. And finally, frontier model from AI services providers such as OpenAI, Anthropic, and Google Gemini is API only, so we can deploy them locally. This is where remote inference comes in as a powerful architectural pattern. The fundamental advantage of remote inference is that it separates Beam pipeline from complex AI infrastructure. This separation allows data engineers to focus on exclusively on data processing and data pipeline, while the challenges of model deployment, hardware management, and the scaling are handled by AI service providers or dedicated in-house infrastructure team. So a separation of ML infra backend offloads the admin overhead from data engineering team. But you must deal with the new challenges with remote inference. And with any remote service, we inherit the classic client-server challenges, which our data pipeline must be robust enough to handle. So we just discussed the problem with the local model and new challenges that remote inference introduces. This brings us to the simple end-to-end pipeline example that I'm going to demonstrate with Gemini and Gemma on Vertex AI as a remote inference example. The rest of this talk will be focused on this P-transform and external API component, how to implement remote inference with Beam's P-transform components. Okay, so now for a quick background on key components. We'll briefly touch on Gemini and Gemma, Vertex AI, and Apache Beam components we need to understand before implement remote LLM inference with Beam. First, Gemini. This is Google's flagship family of powerful multimodal large language models. They understand not just text, but also multimodal media like images, audio, and video. And as of today, these are the latest GA models available. And the Gemini models are incredibly performant, as you can see from the latest AI leaderboard as of June 30th. Gemini 2.5 Pro ranks the top across a variety of tasks for the AI leaderboard. Next is Gemma. Gemma models are lightweight, open models built from the same technology as Gemini by Google DeepMind. They are performant for specialized use cases and can even be run on a device. So it's also possible to deploy it, locally, like for local inference. And also, Gemma can be fine-tuned on your own hardware. We have multiple variations of Gemma models trained for a variety of use cases. Both of these models are available on Vertex AI. So just for convenience for this session, I use Vertex AI as a deployment platform example. And on Vertex AI on GCP, you can build, deploy, and scale models, providing a managed environment for training and inferencing. Okay, so now let's look at the Beam's option to implement remote inference. I will compare 3 P transforms for calling external APIs, starting with Purdue, which is the most primitive transform with Beam. The second one is RequestResponseIO, originally developed for web APIs. And the third approach is RunInference, created for ML inference. This year with Beam 2.65, RunInference added a remote model inference support with remote model handler. And since Beam 2.65 this year, Vertex AI model handler JSON has become a subclass of remote model handler, although it was originally a subclass of model handler in previous Beam versions. And the Gemini model handler was added in the latest Beam 2.66, just released July 1st. So let's just start with Purdue. This is just a quick review. So Purdue is the most fundamental transform, and it's a building block for any element-wise operation in Beam. You can write your own function, do fn, and it gets applied to every element in the input P collection. It's simple and versatile. However, for calling remote API, Purdue leaves everything to you. So you need to really implement everything on your own. There's no automatic retries or backoff. You have to write the logic yourself. There's no built-in batching or boilerplate for handling clients and errors. So next, RequestResponseIO, created originally for easy access to web API. RequestResponseIO was added to Beam since Beam 2.52 for Java and 2.55 for Python. So actually, it's newer than RunInference, which I will talk next. It's a P transform specifically designed for reading from and writing to web API. We need to implement a caller that encapsulates the API call logic in order to call external web API. And RequestResponseIO comes with parameter support for things Purdue doesn't provide, like timeouts, backoff, retries, and even throttler. But we still need to write a custom caller class specific to the web API. and then using those parameters. So just let's look at the default throttler used by RequestResponseIO. As you can see here, default parameter values of default throttler actually pass to adaptive throttler in the background. By default, the window MS and the bucket MS parameters are set to 1 millisecond. And then I will just explain it, the effect of this parameter setting in the next slides. So just before going to that, I would like to quickly touch on adaptive throttler, which is implemented in Beam and used by RequestResponseIO through default throttler and RunInference directly. So RunInference directly call adaptive throttler, but RequestResponseIO is actually calling adaptive throttler through the default throttler. And it works, adaptive throttler works by enforcing a very simple rule, which is the number of client requests should be less than or equal to multiplier k times the number of server accepts. And with Beam's implementation, this multiplier k is set to 2. If request exceeds this, the client throttle itself. Reducing k makes throttling more aggressive. Increasing k makes throttling less aggressive. So going back to the default throttling setting for RequestResponseIO, this tiny window of 1 millisecond is actually disabling the adaptive part of the throttler. So it means the default behavior is just a simple reactive backoff. When a request fails, it just pauses for 5 seconds. It doesn't proactively slow down as the failure rate increases. For the intelligent behavior of underlying adaptive throttler, you need to manually configure the parameter of default throttler. Okay, so next, finally, RunInference, which is a P-transform optimized for efficient use of ML model. So yeah, probably many of you know, RunInference is originally created for local inference. So RunInference was actually supported before RequestResponseIO was added to Beam. So it's been supported since Beam 2.40, and actually it's June 2022, no, not 23 in the slide. So just let's take a look at the parameters. So here definitely, the most important parameter is this model handler. In order to use RunInference, we need to pass the model handler object. And then this is a base model handler class. So it defines how to load the model and run with RunInference with the RunInference method. So as model handler was introduced for local inference for Beam 2.40, there are many built-in model handlers for local inference already created. So we can find the model handler for PyTorch or TensorFlow or scikit-learn, etc. But what's really exciting for us for remote inference is this new remote model handler subclass introduced in Beam 2.65. Actually, that was before I submitted my original talk proposal for this conference. So I needed to actually, adjust my talk after this release. Its subclass is called Gemini model handler. and Vertex AI model handler JSON. These are the one I would use for actually implementation. Just quickly touch on like a remote model handler. It's a subclass of model handler, and it abstracts away the complexity of calling external ML API from RunInference within a Beam pipeline. So this is basically the base model if you want to create your own remote inference model handler. And then, just to quickly take a look at parameters. Here's a key difference from a RequestResponseIO with custom caller class. A remote model handler provides a set of parameters for resilience for ML inference, and it has built-in retries or intelligent adaptive throttler configured out of the box. And looking at the remote handler's parameter setting, you can see the default window set to 1 second, so which is actually 1,000 times longer than the 1 millisecond we just saw with RequestResponseIO, and then this means adaptive throttler is enabled by default. But I think this implementation is still in early stage, and then I think 1 second is probably will be good for traditional ML model. Probably latency is a sub-second, but LLM latency tend to exceed like a second, sometimes 10 seconds, 20 seconds, even minutes. So we need to be careful with these parameters, and probably I haven't experimented, but these are the parameters we need to experiment with LLMs. And then these are the built-in method for remote model handler. So with the Gemini model handler and the Vertex AI handler JSON, you don't need to implement this; it's already implemented. But if you're creating a new subclass, for example, new VLLM remote inference handler, like you have to implement this method. So it's very critical to understand for custom new model handler implementation. So to summarize, these three approaches with Purdue, you build everything yourself. With RequestResponseIO, you get some help, but still need to configure the throttler. And the RunInference and the remote model handler, you get automatic retries, adaptive throttling, and pre-built handler out of the box to start with. And then just a quick note on runner. Just in this session, I don't touch on all the runner specific thing. It gets way too complicated to cover in this single session. So just finally, I'm gonna go through the implementation. For our pipeline implementation, I walk you through the RequestResponseIO example first, and then Gemini model handler and Vertex AI model handler next. So just before starting, we really need to install the packages, and then we definitely need that Beam 2.66 just came out a few days ago, and then actually I couldn't add here, but for Google GenAI SDK, we need 1.21 version. 1.22 or higher has some issue. So with Beam 2.66. Then, this is basically the raw API with the GenAI SDK. You don't need to call this, you use this directly, but just as a reference. And then for Gemma, before calling API, we need to deploy the model. And here's a screenshot of Model Garden on Vertex AI. So you need to just make sure to deploy that first. And then this is a Vertex AI Python SDK example calling the endpoint. So first, let's implement with RequestResponseIO for Gemini. And then, so with RequestResponseIO, we need to implement a custom caller. And this is probably the most primitive implementation. I just borrowed from the Beam page. And then, pipeline code will look like this. But it's still very primitive implementation. It's missing, it's not production ready at all. And then to get the true adaptive throttling, you could definitely change the, default throttler configuration. So, but still, without the implementation, you are missing the custom logic for retries and back off inside the custom caller class. Now let's see how to implement RunInference. Just start with Gemini model handler. And then, this is a Gemini model handler parameter list. But just to start with, what's important is model name. This is where we pass Gemini, 2.5 Flash or Pro, whatever, and then request function and API key. You don't need it. For Vertex AI, you need a project ID and the location with Vertex AI. And here's a pipeline code with RunInference and the Gemini model handler. You instantiate the Gemini model handler, specifying here Gemini 2.5 Flash, and pass it to RunInference. That's it. And then this actually works. Then next with Gemma, with Vertex AI model handler JSON. This is again just a parameter list review, and then with Vertex model handler, there's no model type because you already deployed the model behind the endpoint. So just to pass that endpoint ID and the project and location from Vertex AI. And then, this is a pipeline code. So instantiate the Vertex AI model handler JSON model handler and pass it to RunInference. It's very similar. And then you can easily customize these parameters. So actually, I didn't mention, but Vertex AI model handlers, JSON, and the Gemini model handlers, a subclass of remote model handler. So you can also pass a parameter from remote model handler. So for LLM, you may need a longer window and buckets and other parameter setting. You can definitely override that. So this is all for the implementation. So let's just quickly summarize what I covered. So for remote LLM inference in modern Apache Beam, RunInference with remote model handler is a recommended approach. It provides built-in resilience and requires minimum code. Use of Gemini model handler for Gemini and the Vertex model AI model handler, JSON for Gemma and other models on Vertex AI. RequestResponseIO is still useful If you really need a custom, like a highly customized caller implementation, and all the code examples are available in this GitHub repo. So with that, I'm wrapping up my sessions.